We will finish off Chapter 3 with Section 3.3, Measures of Relative Position. Finally, we can evaluate the position of a data value in relation to the other data points in the set. Often it is useful to know exactly where a particular value is located within a set or the number of values that are above it or below it. We can divide an ordered array, remember that's just arranging our data from smallest to largest values, into equal parts and state in which part the value lies. Dividing the data into 100 parts are called percentiles. These tell us approximately what percentage of the data lie at or below a given value. An example, standardized test scores such as ACTs use percentiles. Medical records often use these as well. If your ACT score of 24 falls in the 74th percentile, this indicates that 74% of everyone who's taken that ACT test are at or below your score of 24. So there may be some values at 24 and the rest will be below 24. So 74% of those values. For this class, we will focus on divisions that divide the data set into 4 parts. The numbers that form these divisions are called quartiles. Quartiles are values that divide an ordered array of data into 4 equal parts, equivalent to the 25th, 50th, 75th percentiles. We will use the following notation. Q1 represents the first quartile. So we use Q for quartile, and the 1 represents that it's our first quartile. And this is the value such that 25% of the data are less than or equal to this value. Q2 represents our second quartile, and this is the value that 50% of the data are less than or equal to this value. Note that this value is the same as our median we found in section 3.1. We go back to the beginning of chapter 3, Q2 is actually our median. And if we remember, our calculator calculated our median. So that's very good news because hopefully our calculator will calculate Q1 and Q3. So finally, Q3 represents our third quartile. And this is the value such that 75% of the data are less than or equal to this value. Let's look at an example. The following speeds of motorists in miles per hour were obtained by a highway patrol officer on duty one weekend. Determine the quartiles of the data set. 60, 62, so these are all speeds of cars that the highway patrol officer used his radar gun on and obtained. We will use what we call the approximation method to find the quartiles of the set. Note that this can be done by hand. However, again, we'll use our TI-84 or NCalc-84 smartphone app to calculate our quartiles. And our key is going to be this 1var stats again. Okay, so here is the technique. Press the stat button, we click edit, and then we input all of our data values into our column L1. We return to the home screen, we press our stat button again, highlight our calculate feature, and pull up our 1var stats command. And then again, we want to input our L1 into our command and close off that command. We hit enter and we see that Q1 is 65, our Q2, which is actually our median, excuse me. So remember that our calculator is going to say this, but we know that these two are equal, and then our is 70.5, and then our Q3, our third quartile, is 78. So pause the video and make sure that you get these values before you continue on. Quartiles are used in a numerical description, aptly called the 5-number summary, because it contains 5 numbers. The minimum value, or what our calculator calls min x, the first quartile, Q1, the median, or the second quartile, remember your calculator is going to denote Q2 as the median, the third quartile, Q3, and the maximum data value that your calculator will call max x. So again, your calculator displays all of these values using the same process as outlined in the previous example. So try finding the 5-number summary for our previous data set. If we want to represent a 5-number summary graphically, we can use a graph that we call a box plot. Some books will call this a box and whiskers plot. Our book just calls it a box plot. So let's suppose that our calculator gives us the following 5-number summary. So we see that our min x is 9, so our smallest data value is 9. Our first quartile is 15.8. Our second quartile, or our median of the data set, is 19.5. Our third quartile is 23.6, and our maximum data value is 42. So we want to create a box plot, so we'll do the following. So we begin with a horizontal number line that contains the 5-number summary. So you want to make sure that you create a number line large enough to fit the smallest data value and the largest data value. So I went from 0 to 45, and I've scaled it by 5 units. Now what we want to do is we want to draw a small line segment above the number line to represent each of the values in the 5-number summary. So remember that our minimum was 9 and our maximum was 42, and then we had our Q1, our median, and our Q3. So I'm going to represent those by dashes right above where they fall on the number line. And now I'm going to connect the line segment that represents the first quartile to the line segment that represents the third quartile, forming a box. So I'm going to connect Q1 and Q3 with a box, and I'm going to draw a line segment down the portion of the box where the median lies. And then I'm going to connect the box. This is why some books call this the box and whisker plot, because these are kind of like whiskers. I'm going to connect the box to my minimum value and my maximum value. And we're done. So this is how we create a box plot using our 5-number summary if we want to. Recall that the range gives the spread of the data. It is given by the maximum value minus the minimum value. We can also find the interquartile range, denoted by IQR. It's very similar to the range, so I take the largest minus the smallest, but now I'm dealing with my quartiles, and so I take my largest quartile minus my smallest quartile. And this is what we call the interquartile range. This is the range of the middle 50% of data, and is seen as the size of the box. So the interquartile range is actually the size of this box in our box plot. Now, let's ask ourselves a question. What if we would like to compare data values from populations with different means and standard deviations? We use what we call standard scores, or we'll see later that we commonly refer to these standard scores as z-scores. These values tell us how far a value lies from the mean, specifically how many standard deviations it is away from the mean. Does this sound familiar? It should, because this is what we did when we used our empirical rule. So the standard score is given by the following. We denote it by z, because we call it a z-score, and it's our data value minus our mean. Remember that in our last section using the empirical rule, this was our distance from the mean, right? We take our value minus our mean, and then we divide it by our standard deviation. If we are given data from the population, we may write the standard score as follows: x minus mu over sigma. Remember that the mean is mu and our standard deviation is sigma. However, if we were given data from a sample, we may write x minus x bar over s. Remember that for a sample, our mean is x bar and our standard deviation is s. Either way, it's always going to follow this procedure. Take my data value, subtract my mean, and divide that number by our standard deviation. We will always write it like this because this sets us up for chapter 6. We'll see this again in chapter 6, and this is how we're going to use it. So we're going to write it like this, using our x minus mu over sigma. If the mean score on the math section of the SAT is 500 with a standard deviation of 100 points, what is the standard score for a student who scored a 630 on this SAT test? So again, what we do is we take our data value, so our data value is 630, and we subtract our mean is 500, and we divide that value by our standard deviation, which was given as 100, and we get the value 1.3. This tells us that a score of 630 is 1.3 standard deviations above the mean, so or to the right of the mean. Let's look at another example. Carlita scored a 32 on the ACT math test and a 730 on the mathematics section of the SAT. If the ACT math test had a mean score of 21 with a standard deviation of 5.3, and the math section of the SAT had a mean score of 516 with a standard deviation of 116, on which exam did Carlita earn a better math score with respect to her peers? So now we have two separate things happening. We have this data value coming from our ACT math test, and we have another data value here coming from another population, coming from the SAT test. And I want to compare these two different data values. So what I'm going to do is I'm going to convert them to my standard scores and then compare the standard scores, because the standard scores take away the mean and the standard deviation. They standardize them so that we can compare them to other values. So when I look at the ACT math test, her data value was 32, the mean was 21, and the standard deviation was 5.3. So I see that Carlita's score was 2.08 standard deviations above the mean. For her math section of the SAT, I take her data value, 730, minus the mean, 516, divided by her the standard deviation of the math section of the SAT, which was given as 116, and I get 1.84. So this tells us for this test, she scored 1.84 units above the mean. So which one did she do better on? This one, because she was more standard deviations away from the mean than this score. So the ACT math test was her better score. Now, you try. So look at this data set and find the 5-number summary here and try drawing a box plot. Try using that technique and drawing a box plot to represent the 5-number summary. And once you've done that, remind yourself how to calculate the interquartile range. This will be good practice before you start the Hawks homework for this section. And once you've done this, try this problem. This one's a little tricky. So Don played in a local golf tournament. So this deals with golfing. So he played in a local golf tournament for charity, and he played in this Pro-Am tournament here. So which tournament did he do better in? with his score. So we have to remember that you may not have played golf before or watched golf before, but we have to remember that in golf, the lower scores are better. So we want the one that's lower, more standard deviations to the left of the mean here. So think about this problem. And again, if you have any questions on any of these problems, feel free to email me.